Hello, my name is Zoltan Frasch, and I'll be speaking about the fundamentals of high-speed PCB design. Here's a legal disclaimer. Please take a moment to read it. Today's agenda, we're going to have an overview of what a high-speed PCB is. We'll have a basic look at the schematics and how the schematics tie into PCB design. We'll take a look at PCB fundamentals. We'll have some examples of component placement and signal routing. Then we'll look at power supply bypassing. Then we'll see what the effects of parasitics on high-speed PCB performance. Then we'll have a closer look at signal routing. Then we'll have examples, and we will close with some summary of PCB do's and don'ts. Begin with the overview. What is high speed? The high speed on PCBs is the frequency above which the PCB can significantly degrade circuit performance. As far as we are concerned, around 50 megahertz and above can be considered high speed. The next question might arise, why high speed PCB? My frequency is 1 kilohertz. I might not need a high-speed PCB. Here is an example. On the left side, to get a square wave at 1 kilohertz frequency, the question is how much bandwidth do I need? So note that if you have bandwidth equal to the frequency of your square wave, you don't get a square wave, you have a sine wave. As the bandwidth increases, you are closer and closer to get a perfect square wave. So how much bandwidth do I need? The bandwidth I need is equivalent to how much rise time do I need. So even though my signal frequency is low, I may need bandwidths up to 100 times my signal frequency. Moving along, the PCB layout is the final step in the design process. And circuit performance is highly dependent on PCB layout. We are going to discuss practical layout guidelines. And these guidelines should improve the layout process, help ensure expected circuit performance, reduce design time, and lower design cost. So let me start with the schematics. A good layout really starts with good schematics. The schematics have two basic functions. They represent the actual circuit connections, which is important, and they generate netlists for layout. So if we stop here, our schematic will only serve the basic purposes. One question arises, can I make my schematic more effective? Can I possibly represent circuit functionality a little more clearly? The advantage of representing circuit functionality is others can understand the circuit. Can I show signal path on the schematics? If I organize my schematic a little more clearer, what is the benefits of showing signal path? It will aid layout. It will aid troubleshooting and debug if it's necessary. It represents functionality. Can I make these schematics more attractive? Is there a value to it? It can increase perceived value. So in closing, the more effective schematics decrease time to market. Here's an example. Here is a perfectly good schematic. It has the two basic necessary functions. It shows the actual circuits. One can count the number of components. It shows the connection. And somewhere in the background, it generated a netlist. Here is an alternative. Exactly the same circuit, slightly rearranged. Note that the components are bigger, easier to read. The functionality becomes apparent. It's your choice which one is better serves your purpose. Let's go to PCB Fundamentals. The basic PCB consists of 3 layers. Here is a copper plane, and it's a contiguous copper sheet, normally 0.7 mils, or if you like 0.02 millimeter thick, or half an ounce. It can be thicker, depending on the design. On top of this copper plane, there is a laminate, and it's made up of woven glass epoxy. Thickness is adjustable. The thinnest usually is 0.05 millimeter or 1.9 mils. The relative permittivity, or dielectric constant if you like, is somewhere between 2.2 and 4.7. The value depends on the material. On top of this laminate, there's a top copper. It's usually a signal layer. It's normally 0.04 millimeter thick, 1 ounce copper. Can be thicker if preferred. On this top copper, there are signal traces, landing pads, and vias etched out. The minimum trace width is normally 4 mils and can be thicker. The minimum space required between 2 objects is again 4 mils, 0.1 millimeter. One thing to note that each trace pad via forms a transmission line with a characteristic impedance. Characteristic impedance depends on the construction, the width, the height of the trace or the shape, and the distance from the plane underneath. Okay, a copper trace, whether it's an actual trace or a pad or a via or a combination, terminated with its characteristic impedance, forms a terminated transmission line. There are advantages to the terminated transmission lines. Signal integrity is not degraded. Unterminated copper shapes form unterminated transmission line. Unterminated transmission lines have capacitance and inductance, and they degrade signal integrity. We have controlled impedance PCBs, and these are manufactured to a specified characteristic impedance, and this is applicable to one specific trace width only. To optimize PCB signal integrity, keeping in mind that the manufacturing will only refer to one trace width, we should keep all long traces the same width, terminate all long traces at the load end with a resistor equal to the characteristic impedance, could possibly double terminate with additional series resistors at the source, but that is not necessary. Double termination would increase the voltage requirement from the output of the last driver. We should keep all unterminated traces as short as possible to reduce capacitance and inductance. We should design pads as small as possible so its capacitance and inductance is minimized. Okay. Next thing is PCB material selection examples. The basic material that everyone is familiar is FR4. These are common general purpose materials. High temperature versions for let V solder exist for an additional cost. The permittivity is reasonably high, 4.7 to 4.2, and this permittivity or dielectric constant generates manageable parasitic capacitances. They low cost, reasonably controlled impedance trace consistency, and is specified to 1 gigahertz. Under other extremes, we can go to the PTFE types of boards. These are high frequency, high temperature material. They have very low permittivity, 2.2 and up. This can reduce parasitic capacitance, so these boards are very good for extremely high frequencies. They are expensive. They have good impedance consistency, and they specify to 10 gigahertz. There are numerous other manufacturers of PCBs rather than Isola or Rogers. Some of the manufacturers show their material with performance specifications similar to these two. Okay, moving on the PCB fundamentals, landing and pad design. First, we talk about the landing pad size. Each part requires a landing pad, and here is an example. Traditionally oversized by about 30% from the component pad. And the picture might look like as I'm showing. Okay. Some of the perceived advantage of oversized pads: can fit soldering iron on it, can allow visual inspection of the solder joint, can accommodate components with larger placement error or components with the next size up. Disadvantages: increase parasitic capacitance, lowers the effective useful frequency, increases the chance of solder bridging because the landing pads are too close to each other in between the two pads, and these require more board space. If we reduce the landing pad size, as shown on the picture, to 0 to 5% oversize, and we look at the pros and cons of that, the mechanical strength retained, so you don't lose any. Contact area between the component and PCB remains the same. It reduces parasitic capacitance, retains higher useful frequency, reduces required board space. Pad shape. Traditionally, pad shapes are rectangular with sharp corners. Examples: if I am to round the corners off, I will be able to do a tighter pad to tray spacing, and that will further reduce board size, especially when the board is fairly populated to a fairly large extent. Okay, now let's look at via placement. Here's a conventional via placement. Here's a resistor, landing pad, and a via connecting one side of the resistor to some plane underneath it. Suppose I minimize the connecting trace. I will have less inductance, less capacitance, and it can result in smaller board space. I can reduce it further, and I can put the via inside the pad. Again, less inductance, less capacitance, smaller board space. Or I can put the via exactly in the middle of the pad, and still less inductance, less capacitance, smaller board space. The disadvantage of this is, as you beginning to close the gap between the pad and the via, there is an increased probability of solder wicking. Solder wicking is when the solder flows out away from the pad down to the other side because of the hole on the via. Very common way to fix this is tented vias, and as you notice on the picture, the last two choices show that the vias are plugged up with conductive copper. Okay. Now let's look at component placement and signal routing. Okay. Just as in real estate, location is everything. So location is of prime importance. Input and output power connections on a board are typically defined. The system will define where they need to be. Component placement and signal routing require deliberate thought and planning ahead of time. First, we look at the plane layers. Here is a piece of laminate. Let's put a plane layer on top of this. Let's put another laminate or prepreg, if you like, and let's put a signal trace on it. And let's see what happens with the current flow. First, we'll put a solder mask. Here is the signal current going one direction. At one point, the signal current will have to return to where it started from. And what happens is the return current follows the path of least inductance. So the path of least inductance is if the return current is exactly underneath the signal current. What happens if you have plane layer cutouts? Here is again a piece of PCB material. Here's a plane layer, and for one reason or another, I was required to cut this plane out. I put another insulating material, then I put my trace on. I put the solder mask on, and here is my signal current. On the return, the signal current will have to go around the cutout and will have to deviate from the being right underneath, and this is not such a good solution. So the conclusion here is to minimize voids in plane layers, make the plane layer as contiguous as possible. Here's another example on signal routing. Here's a system consists of a connector, some high frequency, some ADC, some analogs, and some digital and some power conditioning sections. Here is a possible signal connection. From the connector goes through the RF, then it goes into an ADC, goes into the digital system, goes back to the connector. We also have power conditioning, where from the connector you connect to the power conditioning and you power up all the sections as required. Make a note that the placement here is not optimized. For an optimized placement, we need to minimize the crisscross. Here is an alternate. If you just rearrange the components, then you might be able to come up to a solution like this where there is nothing is crisscrossing. Here's a different way to express this. Here's a piece of PCB. Here's an input connector. Here are some components. There are some more circuitry, some analog, some digital and clock circuits. Here is the equivalent drawing. The analog circuits and the digital circuits are powered from two different supplies, but they have to have a common return. And the PCB will have a resistance and an inductance. Question is what happens. Analog circuitry goes through like that from the connector. Digital circuitry goes through as shown here. Note that the digital circuit is going to make an additional voltage drop on the analog circuits, and the effect of this is that the sensitive analog circuitry is disrupted by digital supply noise. There's an alternate to do this to this, and a slightly arrangement will remove the effect of the digital circuit on the analog. To be able to do this properly, use ground and power planes to reduce the return path, resistance and inductance. Use separate analog and digital ground planes. Compartmentalize the functions. Group the components associated with functions together. Place the functions to coincide with the signal path. And then route the inputs and the outputs along the signal path, and then route the connection between functions as the last step. Packaging. Packaging on high-speed PCBs play a large role. Here's an example. There is an SO8 package, a SOT23, and an LFCSP, and notice that the size between SO8 and SOT23 or LFCSP, there is a marked difference between them. The smaller packages have improved high-frequency response, compact layout, lower package parasitics. There is also low distortion pinout. Some components have a dedicated feedback where the feedback is brought out to a pin near the inverting input of an amplifier so that the wire and the resistor connection that you would normally do from the output to the input is minimized. Layout is more compact, streamlines signal flow, and reduces distortion. Here's an example of a CSP and SOIC package distortion, and note that the improvement is 10 dB at 1 megahertz and 14 dB at 10 megahertz. Here's an example of component placement and signal routing. This happens to be a differential amplifier. There are two inputs to a differential amplifiers, and note their carbon copies to ensure balance. There are gain and feedback resistors. They happen to be located at the yellow area. Again, carbon copy to ensure symmetry. There are two output wires or connectors. They again, carbon copies to ensure symmetry. There are level shifting in this particular board tapped into the signal path. Again, carbon copies to ensure symmetry. There's an auxiliary function on this. This doesn't need to be symmetrical. Here's the signal flow from input to output. The signal path in this case is as short as it is possible. And because it's a differential amplifier, there's a second signal path, and it's identical to the first one to maintain balance. Here are some more examples. On the top, there's a perfectly good high-frequency PCB. Several things to note. There's an excessive number of unnecessary vias. The plane layer underneath the vias is being perforated. There are unnecessary long signal traces. The plane layer on the top is cut out, and there is a large void in there. And in this particular board, there are no internal plane layers, so you're relying on the planes that are chopped apart on the top. Same circuit as the above one, but this circuit has provisions for an auxiliary function. Is this a better alternative? There are more components, yet smaller board size. Vias are minimized. You hardly see any vias. Several internal plane layers. And the landing pads are sized for a 5% over rather than 30%. Here's another example on that same board. There are two resistors located on the board, and they're shown in yellow. And there are two types of PC board materials used for this particular experiment. One of them is a TG170, and the other is a HR370. These boards are 6 layers. Notice the TG170 has a larger overshoot than the HR370. Now, if I bring these two resistors a little bit closer, as shown, note the marked improvement. This means that the length of traces have been reduced, and the improvement is markedly noticeable on the TG170, but it's also some improvement on HR370. Okay. Let's look at the PCB performance. Here is the 2-layer FR4. There are 4 bypass caps shown there. The top ground plane is segmented as we showed before. There is a plane cutout as shown. There are many stitching vias. Here's the equivalent with the 6 layers, TG170 and HR370. There are no bypass caps on this. There's no ground plane on the top. There are no plane cutouts internally. There are no stitching vias required. And the board is smaller size. And here is the response. They all flat, up to about 1 gigahertz. At first sight, the 2-layer FR4 might look like it has a slightly higher bandwidth than the 2 6-layer boards. If we zoom in around the corner, around 1 gigahertz, note that the HR370 in this particular case happens to have the best gain flatness, and the FR4 has a larger gain peaking, and so is the TG170. Let's look at power supply bypassing. It's essential to high-speed circuit performance. It's almost required. It provides a low impedance source and return paths to high-frequency changes in load current. Capacitors as close as possible to the supply pins of each IC provide localized bypassing. Unfortunately, capacitors self-resonate, and as we will demonstrate in a second, not all capacitors are equal. Okay, capacitor has a model, the equivalent series resistance. Capacitance can be calculated as shown. There is an equivalent series inductor, and the effective impedance of this capacitor at series resonance is where XL is equal to XC. Picture is shown. So for any particular capacitance, the impedance of this capacitor optimized at only one frequency. And below or above that frequency, the impedance goes higher, so the capacitance has a lesser effect. Here's an example of several capacitors shown on the same picture. Note that each capacitor has a sweet spot in the frequency range, and their effectiveness is optimized at one particular frequency. So if you want to have a broadband effective bypassing, you will need more than one kind of capacitor. Here's an example of a 0.1 microfarad capacitor. If I pick the 603.1 microfarad, notice the capacitance at 1 megahertz is 81 nanofarad, and the resonance frequency is 18 megahertz. If I picked another 0.1 picofarad capacitor, larger size, but the capacitance at 1 megahertz is now 92 nanofarads, which is a big 10% increase, and the resonance frequency is 23 megahertz. Here's an example of multiple parallel capacitors. PCB by itself is the green line. Notice that it has a high impedance. If you put one set of capacitors, 330 microfarad, 1 microfarad, 0.1 and 0.01 microfarad, you will see the peaks and the valleys. If you double them, then the impedance will go further down. So there is value to add more capacitors. Here's the example of the bypass capacitor placements. Two tantalum capacitors connect close to the supply. Chip capacitors provide bypassing for high frequencies for the area, and chip capacitors close to the IC is for localized bypass. There's an alternate way to do bypassing, and that is to use interplanar capacitance on the PCB. The example of the differential amplifier 6-layer PCB is shown here. There are some inner copper layers placed very close to one another. Interplanar capacitance might be able to replace most discrete bypass caps. Interplanar capacitance is uniformly distributed. You don't need localized bypassing then. An example on the plot shows the bare board input to output. Notice that the 6-layer board has a marked improvement between 100 megahertz and roughly 700 megahertz of at least 20 dB versus the 2-layer board. Here's another example of power supply bypassing. Note that the 6 layers interplanar capacitance allows a noise floor that is, in this case, is nearly 6 dB lower. On the left-hand side and on the right-hand side shows that the noise floor can be driven down by about 3 dBs using interplanar capacitance versus discrete. Here's a plot of what happens with the power plane capacitance. If the power plane is solid, you can have nearly 500 picofarads per square inch of PC board with 2 mils thickness. If you perforate the board and you're only covering 85%, then the interplanar capacitance reduces to about 370 picofarads per inch squared, and as you cutting out more and more of the plane, the capacitance decreases. Let's look at parasitics now. Parasitics take the form of hidden capacitors, usually don't count on parasitics, and they always degrade or distort performance. Let's look at the trace and the parasitics. Okay, here is a two copper layers separated by an insulating layer in between, and this is a power ground combination. Here we put a large spacer to separate the power planes from the signal. Here we put one layer and a spacer, and here we'll put a pad. And then we finally finished with the solder mask. If I remove the power planes that are separated from the signal plane, then I end up with the effective pad to next plane interaction. Every unterminated trace has a capacitance and an inductance, and the equation to calculate this is shown here. And here is an example. If we choose an FR4 PCB with a 1 ounce copper, and we need a 50 ohm controlled impedance for, say, 10 mils wide traces, which are fairly common. If I allow the relative dielectric constant to be 4.7, and I'm going to allow the thickness to be between 0.16 and 0.13 millimeters, then I can have an SOIC landing pad, size is shown there, to exhibit a 0.17 or 0.21 picofarad capacitance and a 0.08 nanohenry inductance. If I change to an LFCSP landing pad, which can be made smaller, note that there is a large decrease in capacitance and substantial decrease still in inductance. So the smaller the pad size has advantage. So to minimize the capacitance of any trace, you want to reduce the trace or the pad area, make it as small as possible, increase spacing to plane layer, reduces capacitance. You can cut the plane out under the pad to further reduce capacitance. To minimize the inductance, in the other hand, you want to reduce the length. You want to increase the width of a trace or the pad. You want to remove voids in the plane layer, which is contradictory to how to minimize capacitance, and decrease spacing to plane layer, which is again contradictory to capacitance. Let's look at via parasitics. Here's a half of a via on the bottom. Here we'll attach a conductor. We'll put an insulating layer on top. We'll put an internal plane layer with a low clearance. We'll put another insulating layer. On the top layer, we put the other half of the via, and we make a connection to some circuitry. We'll put the barrel in to make the connection between the top and the bottom layers, and we finally put some solder masking on. This is how the cross-section of a via looks like. If I just pull back the insulating layer so you can see some visibility, note that the via has an inductance and it has a capacitance, and the equations on how to calculate them are shown there. Here's an example of a 10 mil via on an FR4 PCB. Note that for this particular via, the inductance is almost 1 nanohenry and the capacitance is almost a half a picofarad. Compare this to a 10 millimeter long, 10 mil wide trace. The inductance of a via is only 1/10, and the inductance, capacitance of a via is a little bit less than that of a trace, but not so much. So capacitance predominates in this case. Make a note that vias are capacitive in signal traces and inductive when you're connecting the vias directly to planes. Vias are usually invisible to signals below 1 gigahertz, so one doesn't really need to be worried so much about them. Component parasitics. On the left-hand side is a capacitor, on the right-hand side is a resistor, and note that each component has parasitics that are both inductive, capacitive, or resistive. How do I simulate? Here's an example. I can put a 1.5 picofarad capacitor to ground onto the negative input to simulate the effect of parasitic capacitance. This is what happens when you do that. You can simulate and note that the parasitic capacitance is going to cause some peaking, and that peaking you can't remove. You can only remove it or reduce it if you reduce the parasitic capacitance. Here's an example of a parasitic inductance. You can put it in series, and in this case it's put series into the non-inverting input of an amplifier, and the result when you simulate that is this. So you want to reduce parasitic inductance as much as you possibly can. Signal routing. First thing is vias in signal path. There's really no hard evidence to their measurable degrading effect up to about 2 gigahertz. Above 2 gigahertz, different story. What vias do is they increase PCB real estate requirements, and here's an example. Here are 3 traces. The middle trace has 3 vias in there. If you keep the minimum required clearance between one piece of copper to the other, the left-hand picture shows that the trace separation has to be substantially more than the right-hand picture. So this suggests that minimizing vias have an advantage, and that is you will require less board space. Next important thing that people many times talk about is sharp corners, 90-degree bends in signal traces. There is really no hard evidence to their measurable degrading effect up to about 2 gigahertz. Sharp corners and 90-degree turns can increase PCB real estate requirements, that is. Here's an example of 3 common ways to make a bend. The first one might require slightly more PCB real estate, especially if the board is very busy. But other than that, they have no effect on performance. Signal routing. We should use ground and power planes. We should connect the paths and planes using via in a pad method to minimize the parasitics. We should always use controlled impedance, plane layer directly under or over a signal layer. We should place components as functional block as close as possible. 0.5 millimeter component to component spacing is sufficient for manual placement with the tweezers. Automated placement machines might require less. Minimize vias in signal trace. The less the better. You can put traces closer together to minimize board space requirements. You want to keep traces within functional blocks on the same layer. That is to minimize vias. Should attempt to use interplanar capacitance for bypassing. In many cases, you will not require additional discrete bypass capacitors. Keep plane layers as contiguous as possible. Should avoid unnecessary vias perforating plane layers. Avoid cutouts in the plane layers for best performance. Keep traces as straight as possible, minimize bends and turns. That reduces board space requirements. Few examples. Here is PCB termination resistors. Many use them. The section of that PCB is highlighted here. Input resistors are close to the input connectors. There is a short transmission line, long unterminated trace length. This is not optimized. A better way to do it, here is another board. And in here again, we are magnifying the input termination resistors as close to first component and signal path as possible. The long termination line or transmission line from the input connector to the termination resistor is terminated properly. This is an optimized situation. Here's some PCB Don't-s. Here is an example of the PCB. Several things to note here. There are too many vias. With those vias drilled right through, the internal plane layer is perforated. Looks more of a mesh than a plane. Its effectiveness is greatly reduced. In this particular board, the copper plating is cheap. There is no resistance to the corrosion. You already see discoloration. Longevity is compromised. IC landing pads, notice the middle has an IC. They are very long. This will reduce increased parasitic capacitance, frequency of operation reduced. Another thing to note here, there is silk screen, but it's not readable. This is really an unnecessary expense. If they can't read the silk screen, it has no purpose. Here's another example board. Note that component orientation appears ad hoc. There are components in all kinds of directions. It's very difficult to follow signal path if you ever need to debug this. Component designator placements is not optimized. The text marking resistors is somewhere away from the component itself. Difficult to locate components during debug. Some more high-speed PCB examples. Here's an example of the differential board. Note that the small signal bandwidth of the optimized 6-layer board is 1.41 megahertz. With a 2-layer board with bypass caps, it's only 976. And in linear terms, this is nearly a 50% improvement, which is fairly large. Here's an example of a schematics and a PCB. The schematics are neat. They show signal paths so people can understand what this board does. The PC board example, this is a simple enough PC board that one doesn't need to have components on both sides. Here's a bare board response as it was shown before. Note that 6 layers with interplanar capacitance gives you at 1 gigahertz nearly a 20 dB increase in board performance by itself. Okay, let's have a little summary here. What you need to do is begin by selecting a strategy and putting a plan in place. Have a power supply bypass strategy in place. Is it going to be discrete capacitors? Is it going to be interplanar capacitance? Is it going to be a mix of the two? Decide how to manage parasitics before you begin. Are you going to minimize unterminated trace widths, or you're going to sacrifice frequency response? Remember, a good layout starts with a good schematic, so prepare the schematic with all the additional pluses to it. Keep in mind that high-speed PCB design requires deliberate thought and attention to detail. Use multiple ground, power, and control the impedance planes. Component location on the board is just as important as where you put the entire circuits. So pre-plan where the components will be located. Take the lead when laying out the board. Don't leave anything to chance. As a designer, the PC board forms part of the circuit. New packaging and pinouts will allow improved performance. Several options for signal distribution. Make a choice, a deliberate choice. And that's it. Thanks for your attention.